So, today in this session we are going to learn the displacement method for the determination of focal length of a converging lens. In this method we are going to see how to measure the focal length of any converging lens. It is not simply biconverging lens, it should be any converging lens. And then we will see about ray tracing and silvering of lenses. So, all these topics will be covered in this session. So, first start with the displacement method. This is in our practicals also. So, in this method what we do is we take an optical bench and fix a screen. We fix a screen here and an object. So, we take an object and a screen and keep it at a large distance on the optical bench and let this distance be denoted by D. A converging lens is given to us. This converging lens, we can estimate its focal length by placing a screen here and placing a light source. If we bring this lens close to the window where light source is coming, and we will see where these rays are focused. So, we get an estimate of this focal length. So, we should keep this D. Suppose this estimated value I got 10 centimeter. So, my D should be greater than 40 centimeter. That means 4 times the estimated length of the focal length. So, we will start with some large value of D, that is 4 times large value of the estimated value of F, and then what we do, we place our lens. This is the symbol of the converging lens. We place this lens and we will move from one end to the other end. So, when we move this lens from here to here, we will find at what positions of lens. Suppose this is the L1 position, the image is formed on the screen. So, this is what we have to do. Let us calculate and develop the theory to do this experiment. So, now let us take this distance, screen is fixed here and we had an object O here, and let us assume this to be the lens position L. This is the lens position. Now, suppose this distance is assumed D, then the remaining distance becomes D minus X. So, let us see at this lens position a image is formed here. So, using lens formula, so we will use lens formula, that is 1 by V minus 1 by U is equal to 1 by F. Here V is equal to D minus X, U is equal to minus X, and F is equal to positive F, where F is the focal length that has to be determined. So, 1 by D minus X minus 1 by X minus X, so it becomes plus F, we have 1 by F. Now, if we write this as D minus X into X, then again X plus D minus X is equal to 1 by F. Here X gets cancelled. Now, simplifying it, let us cross multiply it. We get dF is equal to xd minus x square. Rearranging xd, x square minus xd plus dF is equal to 0. So, using lens formula, we got a quadratic expression. This is the quadratic equation. Now, this quadratic equation tells that x has 2 roots. Now, this is a quadratic equation. This is a quadratic equation which tells us that there are 2 values of x. There are 2 lens positions, say x1 and x2. That means there are two positions of lens for which for this object on the fixed screen we are going to have image. Let the two lens positions from this object be denoted as x1 and x2. So, x1 plus x2 is equal to sum of the roots is equal to minus b by a, that is d, and product of the roots x1 and x2 becomes c by a, that is df. Now, here again there are three conditions. One, the roots are imaginary. Next, the roots are real and distinct. And another third condition, roots are real but they are equal roots. That means only one x1 and x2 have the same value. So, we have three conditions. So, now the roots will be real if discriminant, here discriminant is b square minus 4ac, that is d square a minus 4a, a means coefficient of x, 1, c means df, 4 df is greater equal to 0. So, 1d cancels out. So, d is greater than 4f. Thus, the distance between the screen and the object must be greater than 4f. So, very important point I got here, that is the minimum distance between the object and its real image formed by a convex lens is equal to 4f, 4 times f. That is why we want this distance to be more than 4 times the estimated value of the focal length. Now, I have the sum of these roots and product of these roots. So, let us see the difference of these two roots, x2 minus x1. So, from x2 minus x1 whole square is x1 plus x2 whole square minus 4x1 x2. Please take down this first. So, now x2 minus x1 whole square becomes x1 plus x2 is d square minus 4x1 x2, that is 4df. Now, let us call x2 minus x1 as delta. So, delta square is d square minus 4df, and so 4df becomes d square minus delta square. So, f becomes d square minus delta square by 4d. So, what we have to do, already d is known, d is fixed, that is distance between O and screen. We have to calculate delta by our experiment. So, what we do, so this is, so in the experiment this screen is fixed and this is the position L1. So, this position is L1 and you see this distance is x1. So, this distance becomes d minus x1. This is the first lens position L1. So, if this is x1, this is d minus x1. Now, you see here x1 plus x2 is d. That means, if I bring x1 this side, x2 will become d minus x1. That means d minus x1 is x2. So, this is how the first image is formed due to the first position of L1. So, there is one more position of L, that is x2 from here, at which image formation will take up. Let us see it. Now, this is the second, this is the screen and the object. So, this is the first position. There is another position of lens. So, when I have moved to here, I get this image. When I have moved to this position L2 such that this distance is given as x2, this is x2 and this place it is x1. So, this is the displacement x2 minus x1. So, by experiment we have to calculate the two positions x1 and x2, and the difference of x2 and x1, that is delta, is called the displacement of lens. So, d is already known, delta you have to calculate, and so focal length of the lens becomes this. So, here one more important point we observe, that for the two lens positions, the distances, this distance becomes here and this distance becomes here. So, a very important point, for the two lens positions, the distances are interchanged. This is very important. Now, let us calculate the magnifications produced by these two. First, please take down this. Now, you see here, if this is the first lens position, this is my screen and we have an object of height h, suppose. This is the first lens position L1. So, the image formed is here h1. We see this distance is x1 and this distance as x2. Now, for the second position, we have this h and the second position is here, L2 position. So, this x1 distance comes here and this x2 distance comes here. So, you see the distances are exchanged. We call this as delta. Now, here in the second case, the image has a height of h2 and this time magnification is m2 and this time suppose magnification is m1. So, if m1, m2 are the magnifications and if h1, h2 are the height of the images in these two cases, and h is the object height, let us relate m1 and m2 and h1 and h2 by h. So, the magnification for first lens position, magnification m1 is given by, that is minus h1 by h equal to this v by u, that is x2 by this distance is minus x1. So, this is equation number 1, suppose I give. For second lens position, we will write m2 is equal to h2, this is minus h2 suppose, this by h, that will be equal to v by u. V is here x1 and u is here minus x2. This is 2. So, if I multiply 1 and 2, from 1 and 2, we get product of m1 and m2 is minus h1 by h into minus h2 by h is equal to x2 by minus x1 into x1 by minus x2. Here I get m1, m2 is equal to this minus minus cancels, h1, h2 by h square, x2, x2, x1, x1 minus 1, 1. So, simply 1. So, we have here got two relations from here, m1, m2 is equal to, and h, you see this is 1. So, h is equal to the geometric mean of the two images. H is the geometric mean root over h1 and h2. So, these are the important two more important points. about the displacement method. So, let us take an example where we are going to use the displacement method. This problem has been asked in IIT. So, a thin plano-convex lens of focal length f is split into two halves. So, you see here, this is a plano-convex lens. Suppose this is a plano-convex lens. We have cut it into two parts and then split it here. So, split into two halves. One of the halves is shifted along the optical axis as shown in the figure. The separation between the object and the image plane is 1.8 meters, that is 180 centimeter. The magnification of the image formed by one of the half lens is 2. Find the focal length of the lens and separation between the two halves. Draw the ray diagram for image formation. So, what is given? This object and the screen is fixed at a distance of 1.8 meter, and we observe that the magnification in one case is 2. We have to calculate this displacement delta. We have to also calculate this focal length f, and then we have to draw the ray diagram. This we have to do. What is given once again? The distance between object and the screen is 1.8 meter fixed, and magnification in one case is given 2, and we have to calculate the displacement of the lens and focal length of the lens. This is what, let us do it. So, now let us see. Suppose this is the first lens position and call this distance as x. For this lens position, we see the magnification is 2. So, if this is my object, here I get 2 times the object image. This image is 2 times this. Already we have seen that the magnifications M1, M2 is equal to 1. So, if magnification is 2 given for this lens position, for these lens positions we are going to have a magnification half. So, when the lens is nearer to the object, then it will form a magnified image here. So, if this is x, it is h. If it is 2 times, that means this becomes 2x, because magnification is v by u. So, if it is 2, then this distance must be 2 times this 2x. Now, you see here x plus 2x is 180 cm. That means 3x is equal to 180 cm. So, x becomes 60 cm. So, what we got? This distance is 60, this is 120. So, if this is 60, this is 120, then you see, let us write it as x is equal to 60 and this 2x becomes 120. So, we also know that the distance are exchanged. So, this becomes 60 cm. And this becomes 120 cm. So, you see this is delta. So, thus the displacement of the lenses is delta, that is 120 by minus 60, that is 60 cm. This is the distance by which the lenses must be displaced. Now, using lens formula, 1 by v minus 1 by u is 1 by f. We have to determine f. V for this lens, v is 120 and u is this side 60, means minus 60. So, I will put here sign 1 by f. So, this is 120, 1 plus 2. So, implies f is equal to 120 by 3, that is 40 centimeter. So, we got focal length, as 40 centimeter and the displacement as 60 centimeter. You see this distance 180 is more than 4 times 40. 4 times 40 is 160. So, this is more than. So, thus we have calculated F and delta, and let us see the ray diagram for this. Now, you see this is the optic axis and these are the two lens positions. You see object should not be placed here, the object should be like this. So, if a ray passing through the optical center, this ray, you see this ray goes undeviated, it goes undeviated, and any ray from here going this way will meet here. So, suppose this is my screen. You see here, this is the nearest lens L1 position for which it gets 2 times the object height. So, the magnification is 2 for this position of L1. Now, for this point, now this point will be here and this is here. So, its image will be like this. This is the first image H1 I say. Suppose this is H. Now, a ray from here will pass undeviated and a ray like this is going to meet here. So, this is the another image of height H2. This will be 2 times H and this will be H by 2, so that the product of magnifications becomes 1. This is how the two images will be formed by two lens positions. This is the ray diagram which is very important. So, now let us see about lens modifications. So, sometimes we modify our lens and let us see how these modifications is going to influence our imagery. Suppose this is our convex lens and here if I place my object and on this screen I get an image here on this screen, suppose. So, so you see I have drawn a ray diagram to tell that where is the image. So, you see this image is formed here on the screen. Suppose I say this is the image, and you see not only these two rays, in fact there are many rays, there are the whole pencil of rays contribute to the image formation. We just require minimum 2 rays to know where is the image formed. Now, suppose I remove this part. So, if I remove this part, that means I have removed this part only. So, what will happen? It won't be that image won't be formed, or image, since image is forming this side, since this portion is not there, so no image will be formed. This won't happen. Image will be formed only here only, but the contribution from these lights won't come. So, contributions only from upper half come. So, you see only the energy from the lower half is not coming. So, what will happen? Its brightness will be reduced, but image formation will take place only. Simply brightness will be reduced. So, cutting this lens, that means the location of image will not be changed. Next, let us see that if I cut and some displaced in this direction, what will happen? Now, this is my convex lens and I have cut it into 2 portions. And if I cut into 2 portions and then I have moved this portion above and moved these portions below. Suppose this is the above portion and this is the below portion. Suppose I had an object here, O. So, what will happen? This will act as if this is a whole lens whose optic axis is here. So this half lens acts as a full lens, but since I have moved it that means it takes out this optic axis above this. So now if this is the optical center here of this lens and this ray goes like this and they meet here, and so you see this is the, so how to locate this position? You see, just this is the optic axis. So this is our object. The object is like this, and so its imagery will be like this. So O will have its image at O1 due to this upper half. Similarly, for this lower half, the optic axis is like this, and a ray passing through the optical center, goes here undeviated, and another ray, suppose here, they meet here. So you see, this is the optic axis for this second lens, lower lens part, and you just imagine that this is the object, so for which image is formed this way. Suppose this object is placed at 2f distance of this lens. This was the lens which we have cut and displaced. So it is at 2f, and suppose I displace it by 2 delta. So this is also delta and this is also delta. So what will happen? This delta is there, so it is at 2f, so image is formed at 2f. So this is delta, this is also delta. This also happens here. You see, this is delta, so it is formed at, so this distance is also 2f. So now this is here delta again, this distance and this. So the distance between this image O1 and O2 is 1, 2, 3, 4, 4 delta. If it is displaced by 2 delta, this distance is 4 delta. So you see, in the previous discussion, what we did, we cut it into 2 portions and displaced it. It was plano-convex. Now here it is. So you see, for an object position on the screen, we got 2 problems. So same lens when cut here was displaced, and so this lens, as if this is one lens and complete lens. So their cutout portions behave like a complete lens. So the 2 lenses can be generated by one by cutting and thus displacing it. So in that problem, the displacement method, the same lens was cut and displaced to form the 2 lens positions. Now let us see, if I displaced it downwards, what will happen? Now suppose I had a lens like this. What I have done, I had cut out a portion of this lens. This portion has been removed. I am going to remove this. So when I remove this, I will get this. The situation will be like this. This will be empty. Then I have brought it here, and then again I have pasted these cutout portions. So you see here, if this distance is 2 delta, then what happens? This point goes below by delta and this point also goes below by delta. Now this is a composite lens which is behaving as 2 different lenses with different optical axis. You see, this is not the optical axis of the lenses. So let us see, if an object is placed at a distance of 2f, where f is the focal length of this length has a focal length f, this lens, and if I have an object initially, point object at a distance 2f, how is the image formed by this composite lens? This is a modified lens. Let us see it. Now this is my lens system. This is the upper half and this is my lower half. This is the object O placed at a 2f distance. Now, the optical axis of this upper half of this lens is here. You recall we have initially cut out this portion, we have cut out this by 2 delta. That means I have brought this point here. That means when this portion is lowered, then its optical axis is also lowered. So, this is lowered by delta. So, you just imagine, suppose I remove this lower half to make it clear that how image is formed due to upper half. So, you see this was my virtual upper half. So, this is now removed. So, this is the optical center and you see this is the 2f position. So, you get an image exactly at this 2f is here 2f and it will be below this. So, it will be O1 and this distance is also delta. So, from this point this distance will be 2 delta. This is delta and so this is delta, so this 2 delta. Now, so once you see this will happen. Now, let us consider this lower part. So, this is the lower part. So, if lower part is there, it's if I complete it this portion, then you just imagine that this is the optic axis of this lower half and the object, this point object is here. So, its image will be formed above it like this. So, its image is formed here. This is O2. Again this is delta and this is delta. So, distance becomes 4 delta. So, this O will have O1 here and O2 here and 4 delta will be distance, and this is how that composite lens system will work. Now, suppose let us imagine a refracting surface, a refracting element with this one as say R1 radius of curvature and this one say R2, and we had an object, point object here. So, this surface has R1 and this surface has R2, but there are certain regions. Suppose this region has a refractive index mu1 and this region has a refractive index mu2. Again, this region has a refractive index mu3 up to here and this has a refractive index mu4. So, the question will be asked, how many images of this point object O will be formed this side? You see, the radius of curvature for all this part, all this part is R1 and all this part R2. So, you see the focal length has of a lens is N2 by N1 minus 1 by 1 by R1 minus 1 by R2 formula is there. So, here N1 is the refractive index N1 and here also N1, but N2 is the refractive index of the medium, this refracting medium. Now, there are 4 types of medium, but all is having same R1 and R2, N1 is same. So, we have 4 types of wavelengths. So, 4 wavelengths are there, its focal length. So, 4 types of focal lengths are there. That means, suppose due to this image, due to this portion, you see this portion acts as a full lens and makes an image I1. Mu2 forms, this is a portion of a lens, but this portion also forms the same image which a full lens can form. Simply intensity will be different. So, I will get another image I3 due to third portion I4. So, They may be here and there depending on the positions. So, each portion which has a different refractive index will give a different focal length, and so it will form a different location of image. So, each will have only 4 images will be formed, because this is not a single lens, it acts as 4 lenses. Now, let us come to silvering of lenses or theory of thick mirrors. Suppose we had a problem in which I had a lens here, converging lens L, and a mirror here. This is a mirror, spherical mirror, and this is my optic axis of the system. So, if I have to calculate where is the final image formed, so what we will use? We will use the lens formula. This lens, in the absence of this, the lens would have formed the image somewhere here. This is I1. So, if this is not present, the lens would have formed the image at I1, but since it is a mirror, so it reflects this light, and because of this mirror, this is the virtual object for which this would have formed a real image here, that is called I2. But what happens? This is the real image due to mirror only, but again here this is a converging lens, so which further converges it, and the final image is formed at I. So, you see, if this is a lens and a combination of mirror, then 2 times the ray passes through the lens. So, 2 refractions and 1 reflection is taking place. At each stage, the ray gets deviated by the system, optical system. Suppose I consider a parallel ray, then it will be deviated here, then again it will be deviated by this, then again deviations. So, the ray will 2 times deviated by lens and 1 time deviation by this mirror will take place. Now, in silvering of lens, what we do? We take a lens and silver this. If I silver this, I can imagine this situation is similar to this situation, simply D has been made equal to 0. If I combine these two such that this distance between them becomes 0, that means they will behave like a silvered lens. We want to develop the theory of the silvered lens. 2 times it is going lens effect, the ray is deviating due to lens effect, and 1 time by mirror. This is very important point to understand how image formation due to silvered lens is going to take place. Now, suppose this is my lens and I have silvered this. So, when a ray goes here, it refracts, then it reflects, and then again refracts. So, 2 times it passes through the lens. So, we can say that this is equivalent to this. First the ray is going like this, and plus it is encountering that refracting surface, it is being reflected, then again lens. So, again it is coming back to the lens system. So, it is 1 time deviating here, first deviation delta 1, deviation here delta 1, then delta 2, then again delta 3. So, the deviation is at 3 stages. So, we define, so thus a silvered lens behaves as a mirror. Very important point, it behaves like a mirror. So, this silvered lens is a mirror, we can call it a thick mirror. Mirror, I will call it a thick mirror. The power, suppose I want to replace this by a single mirror, so we have to use this as sum of these three components. So, we can say power of equivalent power will be given by the power at each stage will be added algebraically. So, one lens. So, 2 times power of the lens plus the power of the mirror. Here important point, the power should be added with their sign. Means if I say lens, so power of a lens with sign means convex lenses has positive power, concave lenses has negative power. Mirrors, power of a mirror, so the converging mirrors, concave mirror, convergent mirror, so positive power, convex mirror, divergent, so negative power. So this is the sign of powers. So this is also expressed in terms of 1 by f. Remembering, please remember that always use the formula in this power notation, because there is a confusion with the power of focal length. You see, if focus is lying this side, it can be negative, it can be positive, and different people will take different sign conventions. But if it is used in terms of power, then this is a standard sign convention, that converging optical systems will have positive powers, diverging optical systems will have negative power. Let us see with the help of examples. Now, let us take the example of this lens. This is this lens plus this mirror. So, this is convex lens, and this is concave mirror. This is convex lens, concave mirror. So, my formula is P equivalent is 2 times P of lens plus P of mirror. So, P equivalent becomes, so this, let us see what is this portion, lens. So, here the lens is convex, and so it has positive power. That means this quantity is going to be positive. What about this mirror? The mirror is concave mirror, so it has this convergence, so it has positive power. Since concave mirror converges light, so it has positive, this is positive, thus total term is going to be positive. So mirror, this is going to be a mirror, this is not a lens, this equivalent is well known that it is going to act as a mirror. So any mirror with a positive power will be a concave mirror. Thus the equivalent system acts as a concave mirror with positive power. So no doubt it is a concave mirror. So you can now calculate, if you want to calculate what is the focal length of the associated mirror, then its magnitude, remember its magnitude will be given by 2 by focal length of lens plus 1 by focal length of mirror. Here put FL and FM, FL and FM without sign, because we know that they are positive. So, what focal length here will get? We will get the magnitude of the focal length. Don't think that this is positive focal length, so it will be a convex lens like that. We know it's a concave mirror and its magnitude will be given by this. Very important about sign conventions and their interpretation. Now come to second example, where I can say that this is the sum of this plus this type of mirror. So, this is a concave lens and this is a convex mirror. So, the theory is P equivalent is 2 times P lens plus P of the mirror. So, let us see what is this term lens. Here the lens is concave lens. This is the concave lens. The lens is concave and has negative power. This is diverging lens whose power is said to be negative. What about mirror? The mirror here, the mirror is convex and which has also, this is again a diverging mirror, so it has also negative power. So the powers thus you see this quantity is negative, this quantity is negative, so P equivalent becomes, this is when you will put the power, these are negatives, so P equivalent, thus the equivalent system behaves as a convex mirror with negative power. So, thus the equivalent system behaves as a convex mirror with negative power. Now, you see, this is a silvered lens. What we have to do in such a problem is first determine type of lens. The type of lens can be determined by calculating 1 by f as n minus 1 by 1 by r1 minus 1 by r2. If this quantity comes out to be positive, that means the focal length is lying this side, it will be a convex lens. And if this quantity comes out to be negative, it is concave lens. So, first step is to determine the nature of lens. Once we have determined the nature of lens, the next process is determine its power. Determine the sign of its power. So, the sign is that convex lenses has positive power and concave lenses is negative power. That means this is determined. Next, determine the nature of mirror and its power. So, its power can be also determined. Now, sometimes it may happen that I get power of lens plus power of mirror. This is suppose positive power and this is negative power. Suppose this is positive and negative and their sum is positive or negative. So, their sum can be positive or negative. So, just by seeing I can't every time say that what type of lens is there. We have to calculate this power and we have to investigate whether the sum of these diopters, the power expressed in diopters, is coming to be positive or negatively. Accordingly, we can determine what type of lens is it. And once you determine what type of lens, then always use that if this is F equivalent, then it will be 2 by F lens plus 1 by F mirror. Put this always with the sign. Without sign, you first determine these signs here only and then put without signs this. Next, let us take an example when this situation is dipped in a liquid. Now suppose this is my lens which I had silvered, and this lens is now dipped in a liquid. Liquid is there. So what we have to do now is P equivalent will be 2 times P lens plus P of mirror. So now we replace this system by this lens plus a mirror, but nothing will happen to a mirror when it is inside a liquid, but when a lens is inside a liquid, it may behave in a different manner. So you see, what is this? This is a convex lens if placed in air. So convex lens is placed in air, but here this lens in here, I won't simply say it's convex lens. Convex lens placed in air with power, as convex lenses have positive power. Now here important point is that if the liquid is denser, optically denser than the glass or the material of which the lens is made, then the convex lens acts as a concave, and if it is concave lens given, concave lens will act as a convex lens. That means sign will be reversed. But if the liquid is optically rarer than this, then nothing will happen and we have to proceed as it is. So sign here minus, if this is liquid, then we have to take minus and then power of that lens we have to use. This modification will be done. Now suppose we have a lens like this with this portion as silvered, and in this part we have put a liquid, suppose water. This is glass, this is water, and this is silvered part. So here P equivalent will be, suppose a ray goes like this and then it comes like this. So it encounters 2 refractions from water lens and 2 from glass lens and 1 from reflection from mirror. So 2 times power of the water lens plus 2 times power of this glass lens plus 1 times the power of mirror. So here there are 2 lenses, so water lens and glass lens will come into play. If there is one more liquid above, then that power of that liquid lens 2 times, because it is deviating 2 times from the concerned lens. So this is what we have to do in this, we did in this session. In next session we are going to learn about ray tracing, how different rays in the optical system can be used for the formation of image. Thank you.